Okay, great. All right, so let's get started because it's 9:30 on my watch. We're going to do lecture 3 today, sort of continuing discussions that we've been having for the past 2 days. The past 2 days, just to sort of remind you, we got motivated to studying the statistical physics of ecosystems. We realized that almost the entire field of theoretical ecology had been looking at sort of simple models like the Rotko-Volterra model in the limit where there were 2 or 3 species. So that's kind of what we spent our time thinking about carefully yesterday, and sort of asking what happens to important properties of ecosystems like their diversity, the ability of species to coexist, the structure of the ecosystem, which is what the fixed point abundances of the different species are, as well as whether or not ecosystems are feasible and stable, right? And so today what we're going to do is we're going to take our first leap into doing the statistical physics of these systems. We're going to now, from now until the next classes, basically work always in the limit where there are not just 2 species, but rather a large number of them. And for us, a large number is always going to be the thermodynamic limit, where the number of species S goes to infinity. And in this case, what we'll see is that, of course, previously yesterday, we were considering parameters such as the interaction parameters A12 and A21 explicitly. Of course, there were just 2 parameters that we had to worry about with these 2 species. But as the number of species grows, that set of parameters is going to just explode, right? And in particular, when the number of species goes to infinity, you're not going to be able to both describe every single parameter and prescribe it, but also, I think from a practical perspective, we actually aren't able to measure all these parameters for large ecosystems, right? So what we're going to do is we're going to take an approach which is very common in sort of statistical physics, especially in complex systems, which is to assume that you can replace any large complex system with an appropriately chosen random system. And we'll spend some time talking about what I mean by appropriately chosen. But what that's going to mean for us is that we're going to think of the interaction strengths and the carrying capacities as essentially quenched random variables. So we're going to think of these kinds of ecosystems, and in particular the generalized Rotko-Volterra model, as an example of a disordered system. Now, I know you're going to do a lot of stuff with disordered systems next week. We're going to get a little bit of a taste this week. And as far as I understand, there's going to be little overlap between what you're going to do here and what you're going to go do there. And so in my last class, I'll describe a little bit of what you might hope to learn maybe in the next week that you could apply to these kinds of models, but we won't really spend time sort of doing that. And our goal again is going to be to analyze what kinds of statistical behaviors or typical behaviors you get in this GLV model, the generalized Rotko-Volterra model, when there are infinite number of species with an appropriately chosen ensemble. And our goal, as before, at least in these classes, is going to be to compute certain statistical properties of these systems. In particular, we're going to care about the diversity of these systems. And remember, we were talking in the first class about diversity being the number of surviving species. Of course, if you start off with infinitely many species, then of course that diversity is going to blow up. And so what we're going to care about in the thermodynamic limit is the fraction of species that survive. So we're going to start off with some S species. That S is going to be very, very large. And just like we saw yesterday, not all of the S species are going to survive, right? Yesterday, there were cases where you started off with 2 species, but only 1 survived. In this case, you can start off with S species, but only some fraction phi of that will survive. And so we're going to care about that. And that's what we're going to call diversity. Phi equals 1 is going to mean all species survive. Phi equals 0 is going to mean no species survive. Phi equals 0.5 is going to mean half the species survive. We're also going to care about stability. So remember, yesterday we spent a lot of time talking about whether or not a particular fixed point that we find is stable or not. And so we're also going to care about that. Of course, now we're not going to be able to do simple invasion analysis of one species or look at just a finite Jacobian. We're going to have to do something more. And so we'll talk about what we do to assay the stability of these systems. We're also, of course, going to look at the feasibility, because remember, there are some fixed points that we can find where at least one of the species has negative abundances, and that's not a physical situation. And so what we'll see and probe is when is it in these systems that you actually have feasible fixed points. And then finally, we're going to care about the structure of this ecosystem, which is the distribution of abundances of all the species that you get at the end. Okay, so just like yesterday, you had a coexistence fixed point where we could explicitly compute the abundance of species 1 and the abundance of species 2. Now, of course, we're not going to be able to explicitly compute the abundance of every single species. What we'll instead replace it with is a distribution of abundances that you get for an ensemble of species. Okay, and the way that we're going to do all of this is through something called the zero temperature cavity method, which is a standard technique in disordered systems. And really the key idea of the cavity method is going to be to somehow exploit this fact that when S is large, when the system size is large, a system of size S and a system of size S plus 1 look very similar. Okay, and so by essentially self-consistently relating a system of size S with a system of size S plus 1, we're going to be able to derive essentially all that we need to compute all these 4 statistical properties. Okay, so that's kind of where we're headed in this class. I don't know if we'll quite make it to talk about stability and feasibility today, but we'll definitely do all of the dressing to compute basically everything else, and we'll learn about the cavity method, and then basically wherever we end off, we're going to talk about feasibility and stability next. Okay? I should add that another goal of ours is going to be to compute essentially a phase diagram for the long-term behavior of this model. And that phase diagram is going to tell us phases or regimes where this model is stable or unstable, feasible or infeasible. So these 2 properties are going to be pretty important as we go on. Okay. All right. Okay. So let's begin. Let me just write down the GLV model again, because this is something we wrote maybe a day ago now. Let's just remind us, we go back to the situation where there are S species, not just 2. And what we came up with last time was a model that looks something like this. Okay, so let's just sort of remind ourselves. N sub I is the abundance of species I, right? And so I goes from 1 to S, where there are S species, right? So there are S such equations. I'm only writing down one prototypical one. And these species basically have these 3 sets of parameters that come with them that determine their growth rate. One is this R sub I, which is kind of an intrinsic growth rate. The one is this K sub I, which is like the carrying capacity of this species. And then there's a whole bunch of interactions between pairs of species. So every time this Aij is going to tell you how species J affects the growth of species I. Yeah, and so of course there are going to be S minus 1 terms in this sum, right? And so yesterday we were doing this for S equals 2, in which case there was 1 term in this sum, right? Okay, and of course, just to remind us, this sum goes over J from 1 to S, except it doesn't include I, because secretly we've included the AII term over here. Okay, all right, and so now we can imagine. So yesterday we kind of set all these Ri's to 1, all the Ki's to 1, and we were only caring about Aij's. And so we found that there were just 2 parameters that we have to care about, A12 and A21. If there are S species, how many parameters do we then need to care about? S times S minus 1. So that's just parameters here, right? There's also parameters here plus S. There's also parameters here plus S, right? So this is an S-dimensional vector. This is an S-dimensional vector. This is an S by S matrix, right? And so that's, you can imagine what happens to this as S goes to infinity. because that's the limit that we're going to be interested in. That's what I'm going to call a high dimensional limit, or traditionally what we call a thermodynamic limit. In this case, we are simply not going to be able to prescribe every single parameter by hand. Okay. So what we're going to do is we're going to use an old trick from the book, which is to imagine that we're going to pull out each of these parameters from some appropriately chosen distribution. Okay. When we do this, are we making the statement that parameters out there in the world in real ecosystems are random and come from the distribution that we are prescribing? Yes or no? No. Okay, so why are we doing this at all? Maybe we can spend 30 seconds talking about, yeah. So has anyone encountered this idea before in something that they've done in statistical physics about taking a large complex system and replacing it with a random system? Is the idea that large complex systems are random, or is it something else? Yeah.
मैं मना कर रहा था
मतलब 10 मिनट की क्लास में mic or something is on Zoom. Sorry, go on. Yeah. Okay. Yeah. Yeah. Okay, so there was one comment about integrating our bar degrees of freedom. That's true, but it's not related to this comment at all. There's a second comment about us not being sure, and indeed, yes, we're not sure. That's why we replaced it. But what are we like? How is that justified? We're not sure about something, so we say. Okay, but we don't know what that distribution is, right? So. Yeah, but you're talking about you're not talking about uncertainty in the dynamical equations, right? We're talking about uncertainty in the parameters. Yeah, so the question, okay, maybe I'll say this again. The question is, what we like the exercise that we're going to do now is that we're going to imagine that these KIs come from some distribution. These AIJs come from some other distribution, right? We're going to prescribe that distribution. And largely that's going to be because we can then do something theoretically with that, right? And that would be fine. My question is, why should anyone care? Are you making an argument for these, the distributions that we should draw these from being normal distributions? Or what are you giving an argument for? So you're saying when S is large, then KIs have to follow a normal distribution. Why? KIs are carrying capacities, right? They can be drawn from, I mean, they come from some biology. They don't have to, I mean, you're saying that the KIs or something like that come from a sum of many independent, identically distributed variables. We don't know that, right? So generally the idea of all these approaches in complex systems is that, of course, you're not quite justified in assuming that the distributions of these parameters, I mean, in sort of assuming something about the fact that these parameters are random variables. The assumption is that in the end, if you care about certain thermodynamic properties of systems, these properties are universal and independent of the distribution from which you're drawing these kinds of parameters. Okay, they kind of only depend on some statistical moments or properties of those kinds of distributions. Okay, so that kind of universality idea is also something that we're going to use here, and you'll see how it manifests in action. So if you've never kind of seen this before, you'll see how that works out, where in this calculation at some point we're going to say, oh, we assume something about the distribution, but actually that distribution doesn't matter. And that's kind of a very similar idea in sort of a lot of other complex systems approaches. So it's not that, oh, things are going to add up and everything's going to average out. It's not that, oh, there's noise, oh, there's this and that, right? It's actually that the statistical properties that we are going to compute for these systems are actually going to be independent of the distributions from which these parameters are being drawn. Okay, so if that seems a bit like a mystery of how that happens, if you've never seen it before, you'll see it now. Okay? Yeah, I get this question sort of all of the time, which is why are we assuming things are Gaussian or this, that, or the other. Eventually, you can completely relax this assumption, yeah? Okay, so with that disclaimer, yes. Do you guys know something about random matrix theory? Yeah, I mean, maybe, yeah, you're talking about the source of universality, right? So, yeah, exactly. So if you all know about Wigner and the uranium nucleus, do people here know about that story? Maybe raise your hand. Like Wigner coming up with arguments of using random matrix theory about some statistical properties of uranium nucleus and level spacings. People heard of this? Maybe people who have heard of this, raise your hand. Okay, it's very small fraction of people have heard of this. Let me come back to that story in a second. I'll tell you that story. It's a fun one. Okay. Yeah, I think the story will be much better told if you guys don't know it in a concrete context. Okay, so let's go back to what we're sort of doing. So what we're imagining is that there are many of these species. Species 1, 2, 3, 4, 5, ... all the way to S. And they're all interacting with each other. So there's some interaction network. Right? And this interaction network is kind of what's encapsulated in the AIJ matrix. Right? The AIJ tells us how J suppresses I. Okay, so what we're going to do is the following. We're going to imagine that these AIJs are random variables. And in particular, we're going to imagine for now, for convenience, that they are Gaussian random variables. Okay, like I said again, we are going to relax this assumption eventually, but it's all just going to be easy and simple for us to think about it this way. And so I'm going to define it a particular way, but these are going to be Gaussian random variables. I'm going to keep writing RV with some mean, which depends on mu, and some standard deviation, which is going to be set by some parameter sigma. Okay, and the way that I'm going to write down these AIJs is the following. So I'm going to say the AIJ is some mu over S. Remember, S is the number of species, plus some sigma times this little AIJ. This little AIJ is a random variable. In particular, this is what makes it a Gaussian random variable, which means we need to define its statistics. And so I'm going to define the statistics here, and then we're going to spend some time talking about what I just wrote. We're going to say the mean of AIJs are all 0. So these are 0 mean random variables. And I'm going to think about moment AIJ, AKL, and I'm going to write it down this way. Again, you've not seen this before. We'll spend some time talking about how to interpret all of this. This is delta IK, delta JL over S, plus rho over S, delta IL, delta JK. Okay, so let's spend some time sort of absorbing what I wrote and kind of interpreting what it all means. Right, so first, just to remind you, these AIJs are now all random variables. So what we're trying to fill up is a full interaction matrix. Right, this interaction matrix A. Over here, the rows of this matrix go from 1 to S. The columns of this matrix go from what? 1 to S. And actually the J's go here and the I's go here. That's our convention for how we write matrices. So what does Aij mean? How species J affects species I, right? So this is kind of like the inhibitor in some sense, if I'm thinking about inhibitory interactions, and this is the inhibited species, right? And just for convenience, we can imagine that we also think about the diagonal entries of this matrix. The diagonal entries of this matrix are kind of already set to 1, so they don't go into this prescription, right? Secretly, what I forgot to write down is that this AII is always 1. Right, so these diagonal entries are always 1, and we're kind of talking about filling up the rest of this matrix. Okay, and so what we've said is that we'll fill up this rest of this matrix with entries picked from a Gaussian with mean. Yeah, what's the mean of this of this guy? What's mean of capital Aij? Is it mu or mu over S? Everyone knows how you find. I don't know if you guys did. Have you guys encountered you must have encountered random variables, right? We're in a statistical physics school. Okay, so I want to get the first moment of this random variable. What do? Take the first moment here, I end up with mu over S, and what does this give me? 0, right? So the mean of Aij is mu over S, right? But I said something about this thing being mu, so I should correct that. That should be mu over S, right? Why might I want to do that? Why might I not want to define it just as mu, where mu is some finite number? Because what is this mean doing as S is going to infinity? It's going, yeah, it's going down, right? It's going to 0 in fact. So why would I want to construct something like that? Have you guys seen this before? These kinds of scaling arguments and defining random variables? Okay, if you haven't, again, this is a nice place to see it. Yeah, so can someone give an argument for why you might, so essentially what we're doing is we have some parameter that prescribes the mean, right? And then we're scaling that parameter with the system size, right? Why might we want to do this? If you're, by the way, in this class, if you're ever confused, and I can see confusion on your faces as we've gone from 2 species to infinitely many, always remember what we did in the 2 species case. We always thought about the equations, right? So if you're confused, just put it back into the equation and see what you get either way, right? So let's just forget about the fluctuations in Aij for a second. Let's just think about all Aijs being some mu or mu over S. What happens to the growth rate of each species? That's some Ki, which let's imagine is 1 for a second. Some Ni, which is some abundance of the species. So that's finite minus finite. And that's a sum over how many terms? S minus 1, which is infinitely many terms, right? So if all of these n's were finite number, or all of the abundances of the different species were finite numbers, what would happen to this sum if Aij's were all mu? You get mu times, let's say all of the n's are also the same in 1. You get mu plus mu plus mu plus mu plus mu plus mu. That just blows up, right? So the growth rate is not well defined at all. The growth rate then blows up, right? Do you see what I mean? You get mu times n plus mu times n plus mu times n plus mu times n S times, right? So you get S times mu times mean n, right? All I'm saying is if you just naively take the mean of this quantity, that will be S times the mean of Aij times the mean of n, right? This is very naive. This is not strictly speaking true because we're ignoring correlations between these guys, right? But for a second, if we did that, If this was finite and this was finite, this would blow up as s goes to infinity, right? So that's what is called not having a well-defined thermodynamic limit. Okay, your entire model is not well-defined. So what can you do? You can imagine that this mean of Aij, because this, of course, you don't have any control over, right? Mean of n is actually an outcome of the dynamics. That's a self-organized quantity, but this is something that you choose. This is something about your parameters, right? So the simplest thing you can do, in fact, one of the only things that you can do, is you can scale the mean of Aij, and there's only one way to scale it, right? You can scale it with, if you scaled it with 1 over s, if you imagine that this was mu over s, where mu was a finite order 1 number, then that would be okay, right? Now this no longer goes to infinity. As s goes to infinity, you have a well-defined thermodynamic limit. Could I have scaled this? Let's just take a quick vote. Could I have scaled this mean by s squared? Ready? 3, 2, 1. No, right? Why is that? It's pretty simple, right? Now the interactions would become vanishing in the limit of large S. And that's the whole point of studying this model, is to ask what happens to the interactions, right? So what's nice about taking this scaling is that now you end up with a growth rate that has mixtures of contributions that are roughly equal size from all things, right? This Ki is going to be some order 1 number. This Ni is going to be some self-organized consequence, but let's say it's an order 1 number. This is also going to be an order 1 number, right? So what this species does on its own and affects its growth rate is going to be as strong as what all the other species do to it, right? So you're going to have some competition between basically growth rate from all the other species and your own self-inhibition. Okay, is that clear? This sort of scaling argument? Okay, so the mean has to scale as 1 over s in all of these systems. And if the mean scales as 1 over s, does the variance also have to scale? Ready? 3, 2, 1. Okay, why do people think it doesn't have to scale? So now we're imagining a situation where the mean of Aij is going to 0, but the variance stays finite. What's going to happen to this quantity in that case? So right now we only thought about the mean of this quantity, right? This quantity itself is going to be a random variable. And so any random variable will have fluctuations. And what's going to happen to the fluctuations if we don't scale the variance with system size? What will remain constant? The fluctuations in each term will remain constant, but what's going to happen? The fluctuations of this entire summed quantity. Are people familiar how to think about random variables and sums of random variables and things of that kind? What will average themselves out? The fluctuations will average themselves out. What makes you think that? Yeah, but we don't know if that would happen, right? So really, what will also happen in this case, also the fluctuations would blow up, unless you scale with system size. You can also imagine if you have a distribution which is a sum of many random variables, if the mean scales as 1 over s, the variance also has to scale as 1 over s, right? So the standard deviation has to scale as 1 over root s, and that's kind of exactly what's written in this in this sort of cryptic form. So let's sort of go about doing this. So the first part of this was just about the mean of Aij, and that scaling is 1 over s. The second part, of course, is the fluctuations. Of course, every quantity here is not mu over s. It's mu over s plus or minus some number. And that number essentially has a scale which is sigma over root s. And so to see this, we have to look at the statistics of this little fluctuation Aij. It is indeed zero mean, right? But this thing over here tells us the following. I guess I have to ask, everyone's familiar with what delta Ik means? Okay, what does it mean? If it's, yeah, it's a Kronecker delta, right? So when I is k, it's 1. When I is not k, it's 0. So yeah, can someone say how we interpret, maybe let's just talk about the first term in this quantity. So this is trying to ask, what's this whole thing LHS is trying to ask, if I take some Aij and some AKL, right, two random entries of this matrix, if I just compare their fluctuations, what's going to be the expected value of the cross moment, right? And what this is saying over here is that it has two parts, right? So what's this first part telling us? Let's just ask when this first part even contributes, right? So when does this first part contribute? When I equals k and j equals L. And what does that mean? When I equals k and j equals L, this is just Aij squared, right? So essentially you're just asking about the variance of this quantity, right? And what is this thing telling us that the variance is? It's 1 over S, right? And that's indeed what we wanted. And of course, there's a prefactor sigma sitting out here. So actually the variance is sigma squared over S, right? Everyone's familiar going back and forth between standard deviations and variances, squares and square roots. Okay, so that's what this part is saying, right? This part is saying something about the variance of little aij. Variance is 1 over S. Okay, what is this part saying? Now I guess you can figure it out. So when is this part non-zero? When I is, yeah, exactly, when you have diagonally opposite entries, right? When I equals L and j equals k, right? What does that mean? I equals L and j equals k, you're looking at aij, aji. That's sort of what it means, right? You're looking at entries that are opposing the diagonal. And what is this saying happens to those? There's an extra bit there, right? The variance of those entries is actually not 1 over S, but in fact rho over S, right? And in fact, what this is saying is that the diagonal entries are correlated. And in fact, they have correlation rho or rho over S. If you can't, I mean, if you're a bit confused by this correlation, I'll leave it to you as homework. Go and look up what the definition of correlation is, and you'll be able to figure out that that's exactly what this should be. Okay, so let's just sort of recap what we are saying about Aij. We've constructed a rather peculiar ensemble. Aijs are Gaussian random variables with mean mu over S, which is something we must have. A variance sigma over root S, sigma squared over S, or a standard deviation sigma over root S, such that you have a correlation across diagonally opposite entries, which is rho. Okay? So really you need 3 parameters to be able to fully describe this ensemble. What are those 3 parameters? Mu, sigma, and rho, right? This whole thing, of course, it has these S square entries, but really typified by just these 3 parameters. Okay, any questions about this Aij? This, of course, is a choice that I've made, right? This is just a choice that I've made to do a calculation. Once you sort of figure out how to compute all of these quantities with this ensemble, you can try any other ensemble that you want to construct, right? All you need to make sure is that ensemble has a well-defined thermodynamic. Okay? All right, any questions? Yes, please. Yes. So what I mean by this is, what do I mean by quench disorder? What I mean by this is that these sort of parameters are random variables that are quenched, meaning that they aren't changing with time. Yeah? So Aij is Aij, right? As opposed to something that's fluctuating. Okay. Any other questions? Okay, so then let's talk about the simpler one, the simpler random variables, which are what? What? Yeah. What are the other parameters that, like, are we all set, or are we left to define some parameters in our ensemble? Yeah, we haven't thought about the KIs and the RIs, right? So what I'm going to do for simplicity is I'm going to kind of forget RI, set them all to 1. That can be our ensemble, that the RIs are some delta function at 1. But we will think about KIs. The KIs will again now be simple. I don't have to think about any correlations. They're just going to be some Gaussian random variable with mean, let me call it K, capital K, and variance sigma K squared. So I'm just going to write them down like this. And the fluctuation, let me just make sure I'm consistent with notation in my notes. Well, okay. Let me just think of this as delta Ki. Okay. Maybe I'll think about it this way. Sigma K, delta Ki. This is saying that the mean of Ki is K, because I'm going to define the statistics of this delta Ki. This is going to be a 0 mean random variable, and it's going to have delta Ki, delta Kj. Do I need to scale this one? Yeah, here I haven't written K over S, right? Why is that? There's only one, right? I'm not summing over anything. In fact, if I had K over S, then I'd be kind of screwing myself up, right? Then that term would play a vanishing contribution. And so what should I write over here if I just wanted this to be a 0 mean unit variance Gaussian random variable? Delta Ij. Okay, very good. Okay, so we're all on board. Okay, we've fully defined our ensemble. We have our entire model. Let's just remind ourselves what we are trying to do, what our goal is. So our goal, again, to remind you, what was our goal yesterday? Once we had all the parameters in our model, what was our first question? Yeah, how many fixed points, right? So let's just ask that question again. How many fixed points do we expect for this system? Maybe you don't have fingers to sort of explain that. So maybe I'll give you a few options. How many fixed points in principle do you expect? I'm not talking about feasibility, stability yet. So is it S? Is it S squared? Is it S plus 1? Is it 2 to the power S? Is it log S? And I think you don't have another finger on one hand, but I'll give an option as 6 as don't know, which you can use your thumb for. Okay? So is the question clear? We'll all vote silently first, yeah? So how many fixed points do we expect for this system of size S? Is it S, S squared, S plus 1, 2 to the S, log S, or don't know? Okay? I'll give you 5 seconds to think about it. You're confused, just think about what we did yesterday and how you got fixed points. Every time I get confused for the S case, I just think about what happens for the 2 case. And that usually tells you how to think about it. Okay, let's take a vote. Ready? 3, 2, 1. Okay, there are mixtures of 2s and 4s, and there's enough of a mixture that maybe spend 20 seconds talking to your neighbor, discussing why it should be one way or the other. Okay, maybe that's enough time for discussion, though I saw the discussion, I've heard the discussion pick up over time. But let's kind of move on. Let's take a little vote again for how many fixed points we think we convinced each other there are. All right, ready? 3, 2, 1. Okay, I'd say some people are still at 2s, but many have turned to 4. There are a few 3s that I see. Okay, so indeed the answer is 4. And can someone say why? Okay. Okay. Okay, so this is, I mean, you have some logic over there, but I hear in this logic a thing that I warned you against yesterday, which is somehow when we think about fixed points, remember I warned you this yesterday, you think about each equation separately, satisfying each equation's left-hand side equal to 0 separately, right? That's not what a fixed point is, right? What do you need for a fixed point? You need coincidence, right? All of the equations must have left-hand side equal to 0. So in this case, the structure of, it's totally true that these are second order, etc., but in this case, the structure of the equations is what allows us to make the argument. I could have constructed a slightly different version of this equation, which would still be second order, but where this argument would not work because because you're trying to individually satisfy each of these equations having no growth or depth. Right? You want to satisfy them all together. Exactly. Exactly. So it's because of the structure of these equations that you kind of factorize out the ni over here and the sort of this thing over here, which is a function of the ni's, that you can essentially ask for any species in a steady state. It can either be extinct, that is ni equal to 0, and then whatever happens here doesn't matter, or it cannot be extinct, that is ni is not equal to 0, and then the only way to be at a fixed point is for this parenthetical term to be 0, right? And because we argued already yesterday that these parenthetical terms all form a system of linear equations, in the end you will have, if S star species survive, you'll have S star linear equations of this type because all the extinct species would just contribute by setting their n's to 0. So you have a system of S star equations, one for each of the surviving species, and how many unknowns? Is it S, S star, S minus S star? I thought I told you everything already. You know a bunch of extinct species are extinct, right? How many extinct species are there? S minus S star, right? And so for S minus S star, these n's are all 0, right? So the only unknowns that I have are the abundances of the surviving species, right? So there are S star unknowns, S star set of ni's or nj's that I don't know, and I have S star equations, right? And since that's a linear set of linear equations, S star equations, S star unknowns, they all have one combined solution, right? So all you need to do is to ask how many such combinations of survivors versus extinct species you can construct, right? So do you see that in this argument, we're talking about the entire system. We're not talking about any of the equations separately, right? Every time you choose a set of S star survivors, you have one and exactly one solution, right? And so how many ways are there of choosing of picking a certain number of survivors? Well, every species can either survive or not survive. So there's two options. So that's 2 to the power S, right? And so that's what gives you 2 to the S. Yeah. So remember, Whenever you're talking about fixed points of dynamical systems, you have to think about the entire system. Okay? Not about each degree of freedom individually. Okay, and so then what do we do once we know something about these fixed points? So there are 2 to the s of them. That means there are exponentially many fixed points, especially as s grows. Right? By the way, you can check when s was equal to 2, you ended up with 4. Right? I guess that's why lots of people thought s square also works. Okay. Yeah. So what else should we care about? Sorry. Stability, but I guess before stability, we care about one more thing, right? Just about feasibility itself, right? Whether the fixed point is feasible or not. If the fixed point is not feasible, you don't care about its stability, right? So these are all questions that we don't currently know the answer to in this system because, well, fixed points will be random. There's an exponentially large number of them. You're not going to be able to compute every single one of them. What we're going to be able to do is to compute the statistics of a typical fixed point, okay? Which means our goal is going to be to compute the following quantities. Like what are the kinds of statistics of that typical fixed point that we might imagine? Is everyone clear what I mean by typical fixed point? By typical fixed point, I mean I draw all of these aij's in this way. I draw all of these ki's in this way. I run these equations. I sort of simulate them to steady state. I end up with some sort of steady state. And now I can measure some statistical properties of this kind of steady state, right? And so by typical, I just mean if I just did it once, twice, thrice, what would I typically see? Okay. You might contrast that with atypical, and atypical would be, of course, like a state that I might see that's nevertheless possible by the equations, but that is not typical. So for instance, we're going to see that a state in which all the species die is possible, but not typical. Okay, and this is, if you are confused about how this can be the case, of course, the simplest example is if I toss a coin that's fair 1,000,000 times, it's still possible that they're all heads, but it's not typical. Right? What is typical is that it's roughly half heads and half tails. Right? So that's kind of going to be our approach here. We're going to compute the statistics of these typical fixed points, and in particular, we're going to compute the following quantities. We're going to compute some fraction that we're going to call phi, which is the fraction of surviving species, is S star over S. Okay, we're going to want to compute whether things are feasible or stable, right? So that's a qualitative question. And we're going to talk about how we figure out whether something is feasible or stable. And then we're going to care also about structure, right? And by structure, we mean the distribution of sort of abundances. And in particular, for now, let's just imagine that we're going to care about the first two moments of that distribution. Okay? So our abundance distribution is going to be some P of Ni, right? Let me actually write it down this way. We want to characterize P of Ni, which is the distribution of the abundances of all these species. And one thing that we might care about this distribution is its first two moments. Maybe we care about the other moments as well, but we'll see that actually in this example, we won't need to care about more. Okay, so is it clear sort of what our goal is? We're going to want to compute diversity, which for us is just going to become a fraction of surviving species. And again, this is going to be the typical fraction, right? Think of it like the number of heads when you toss a coin. Of course, that's a random variable, but there's going to be a typical number. And we'll make that idea more precise in terms of something called self-averaging. We're going to care about feasibility and stability, and then we're going to care about the abundance distribution. And the way that we're going to do this is using something called the cavity method. So how many people here have worked with the cavity method, used the cavity method before? Okay, none of you. Okay, so great. So then I'm not preaching to the choir. We'll all learn this together. Okay, so the idea is the following. What we're trying to do is really to solve a large random nonlinear set of equations, right? We care about, for a second, let's just care about the steady states, right, the fixed points, because that's kind of what we are worrying about. We end up with a large system of random nonlinear equations, right? And we need to solve them simultaneously, right? And so this we can do using this method. And really the method is going to be very algorithmic. So I'm just going to kind of sketch out in a picture what the algorithm of this method is like and what the idea and the approach is. And then we'll go through all of the steps of the method mathematically for this model. Yeah, the hope is going to be that as you see the algorithm and as we execute it, you're going to learn the algorithm enough that you can execute it for any other model that you want. Yeah, so this is a trick that you can kind of learn that you can apply to other systems, but we're going to learn it in the context of this GLV model. So the idea is that you have, again, this system of S species. So you have a system of size S. And of course, there's going to be some interactions between these species. And what you're going to do is we are going to assume that this system is at steady state. And again, in the lecture on Friday or tomorrow, we're going to relax this assumption. But for today, we're going to assume that it's at steady state. We care about fixed points. That's going to be our step one. Our step two is going to be to add a new degree of freedom or a new species to this system. And that species is what we're going to call the cavity species. Okay? So we're adding this other species, and actually to index it, I'm just going to use the index 0. It's like the 0th species, even though it comes later. Right? I'm just going to put a little cross on it just to remind us it's a cavity species, and also because 0 looks very much like this circle. And once we introduce this cavity species, what do you think is going to happen to the system? Once you introduce the species, is it going to remain at this same steady state? Yes, why is that? Again, don't think about wishy-washy stuff that you have in your mind. Think about what's happening in the equations. So would something change about the equations? So for all the survivors right now, this term in parentheses is 0, right? And so once you add this other cavity species, what would happen to these equations? You would add another term, right? Which would depend on how this cavity species inhibits all the other species, right? So this cavity species also affects everyone else. And in fact, what we are assuming is actually that the cavity species is statistically identical to every other species in this system. This is going to be a really important assumption. Right? And what does it mean for the species to be statistically identical? The KIs and the AIJs are drawn from the same distribution as everyone else. Right? So it's going to affect all of the other species. There's going to be extra terms that are going to show up in everything here. And as a result of this, this system is no longer going to be at steady state. It's going to become both a system of size S plus 1 and something that's not at steady state. Right? So this is going to give us an S plus 1 species system, not at steady state. And so what we now want to know is what's the new steady state that this system of size S plus 1 is going to go to. Okay? So to do that, our third step is going to be to actually explicitly compute the effect that this cavity species has on all of the other species, kind of ask what happens to that, right? So this is effect of cavity species on all others. And here we're going to use the fact that this system of size S was large to sort of begin with. And so this cavity species is going to exert a small effect on all of the other species. It's not going to be a negligible effect, but it's going to be a small effect. Because this cavity species, we'll see, acts as a small perturbation to the growth rates of all the other species. And so what this is going to mean is that it's going to allow us to use linear response theory. Which means that we are going to be able to write Nj, which is the abundance of species, let's say, after the perturbation, in terms of approximately Nj without zero. Right, so I'm going to keep using this term, terminology. If I say without zero, that's just going to mean what things were like before when we started off. So for here, I'll write down before, but I won't keep writing down before and after again and again. So when I say Nj, that's going to mean what happens after the perturbation. When I'm going to say Nj without zero, or Nk without zero, or Ni without zero, that's going to be stuff that was there in the steady state before the perturbation. The idea is just that I can kind of relate those two by some delta Nj. This delta Nj, we're going to be able to write down explicitly. This is our effect of the perturbation. Okay, so thus far our logic is we have a system of size S, introduce a cavity species affects all the others, which changes all of their abundances by some amount that we will compute. This is all at steady state, so I can put stars on it if I want to remind myself. Have I now attained the steady state of the entire system of size S plus 1? Yeah. Yeah, this is static linear response. So remember, we're mapping steady states to steady states, right? So this Nj without zero star is a steady state abundance of species J before the cavity species was introduced. Nj star after is a steady state abundance after the cavity species is introduced. Thanks for that clarification. Okay, so I have this for S species. So I can kind of say something about the abundance of the S species after the perturbation, but I need one more, right? What do I need? Okay, everyone's a bit lost. What's the abundance of the cavity species? That you can't use linear response for, right? Why is that? A, the cavity species didn't exist before the perturbation. The cavity species didn't really perturb itself, right? So that's a different thing, right? So to complete this, our fourth step is going to be to use the fact that once all of these species are perturbed, they all affect this cavity species back. And we can use this effect back of all the species to compute the abundance of the cavity species at steady state. That's something that we can call N0 star. And again, I'm not going to keep writing the star again and again, but I'll write it now because I just want to emphasize that we're only mapping steady states to sort of steady states. And this is going to be coming from the fact that all other species affect N0 back. Okay, and at the end of this, what we're going to do is in our last step, we're going to do something that will seem a bit odd and maybe magical if you've never seen it before. But that's really what makes it work, which is that we're going to now end up with a self-consistent equation for the abundance of the cavity species or N0, which we can actually solve. And get the statistical properties, or get basically P of N0, which is the distribution of the abundances of this cavity species. And at the end of this, you might say, hey, well, you computed the distribution of some random species, but this is where this fact is going to come in. So in the end, we're going to invoke the fact that the cavity species was actually statistically identical to all of the other species. And so when you have a large system, whatever we computed for the cavity species is actually exactly the same as what we're going to expect for all the other species. And so indeed, P of N0 is P of Ni. Okay, I'll say this again, and if you're sort of confused about what all of this means, it'll become clearer when we do it in context. But the cavity method is really about starting off with a large system to begin with, size S. Assume it's already at some steady state. You introduce a cavity species which is statistically identical to all the other species. Your goal is to then compute the new steady state of this system of size S plus 1. That involves two parts: computing the abundances of the other pre-existing species, which you will do using linear response, because the cavity species, as we'll see, is going to be a small perturbation, and the extra degree of freedom that we introduced, which is the cavity species itself. And in the end, we're going to use the fact that all other species affected back. And in the end, we're going to end up with a set of self-consistent equations, which is going to let us say everything we want to know about the statistics of this cavity species abundance. And then finally, we're going to use the fact that actually, we're going to forget that there was this cavity species to begin with. There's nothing different about like once S is large enough, it doesn't really matter whether this was a cavity species or any other species. And so indeed, the statistics that we compute for the cavity species are going to hold for every other species. And again, maybe at the end of this calculation, it will still feel kind of disbelieving to you. And then, of course, you can kind of try it out yourself by doing numerics and seeing that it really, really does work very, very well. Okay, is it clear what we're going to do in the last 25 minutes of this class? All right, so let's do it. So what I'm going to do basically here now is just act out that algorithm for our GLV model. And I'll leave this orange thing over here just to remind us what our goals are. Okay, so let's see this in action. Let's first do step one. Step one is to start off with our system of size S plus 1, S, before we introduce the cavity species. So what we have is all of our species are at some sort of steady state. So I want to write down the dynamics of Ni dot. That's 0. You have this species, you have this at steady state. And I really care about Ni without 0, right? I'm trying to compute everything without the cavity species. This without 0 over here is always the term, the sort of subscript that I'm going to use to remind myself of that. So now if I just write down my Lotka-Volterra model for this guy, that's what I'm going to get. Is everyone okay with this? I just wrote down the GLV equation just with these without zeros again and again to remind me that I'm looking at the system without the cavity species first. Okay, so that's my system of size S at steady state. Steady state comes from the fact that this is 0. Okay. Okay, now let me do maybe step 2, which is you introduce the cavity species. Now we're not in the without zero situation. And let's imagine what's going to happen to all of these species, right? We're going to end up with a new steady state. And I dot is again going to be zero. And remember, and notice that now I've not written the without zero anymore. To remind myself that I'm not in a situation without this cavity species. But again, there'll be some new steady state. And in this new steady state, I'll satisfy the following equation. I guess this ki without zero is not something I need to write because ki's are just parameters. They're going to say the same thing here, aij's. Is that it, or have I missed something? Exactly, I've missed the effect of the cavity species, right? There's one more term which we'll write down explicitly, which is ai0 ends n0, right? That's the extra inhibition that we get from the cavity species. That's in essence the effect of the cavity species, right? This is going to be some new steady state. Of course, we don't know what these ni's are and what these nj's are. So how can we think about the effect of this cavity species? Like, what has it really done to the equation of motion for the species I? It's added this term, right? And so just notice the fact that really you can just think about this term as essentially changing the ki, right? You can just think of this as a ki plus delta ki, where delta ki is essentially this minus ai0 n0. It's as if you've reduced the carrying capacity of each species by some random amount, right? Whatever steady state you get for that is actually what you would get for this system, right? And so now let's ask ourselves whether this delta k, like what this delta ki is compared to ki. Right? So this ki is going to be, it's going to have some mean k, which we can imagine is order 1. What about this guy? This n0 is again maybe going to be some finite order 1 number. And this ai0, what's the magnitude of this? Is it order 1? It's order 1 over s, right? So this term is roughly order 1 over s. This term is roughly order 1. And so really this is an order 1 over s roughly correction to the ki, right? In the limit that s is large, this is a small perturbation, right? So essentially, you can think about the cavity species, and this is, I guess, step 3, which is the cavity species is a small perturbation to the carrying capacity of all species, of all pre-existing species. And this is going to allow us to use linear response. So what we can write down, let me make sure that I have the same notation as what I'll use later. Let me write down it for nj. So nj, and again, nj star, because I'm looking at what's happening to the steady states. I haven't been writing stars here. nj is nj without 0, the sort of steady state abundance I had before, plus just this thing. Okay, let's go through this together to make sure we understand. Is everyone familiar with linear response? I'm going to assume that all of you are familiar with linear response. But essentially, all we are saying is that nj was some function of the k's and n's and so on and so forth. And what you essentially did was perturb the k's by a little bit, right? What that bit was, we don't, well, it's that, and it's some random number. But essentially, what that will do is if that perturbation is small, then we can just expand nj to linear order in the perturbation, delta KK, and this actually I should, maybe I can just write down this as delta K. This is little k, this is capital K, sorry about that. And all we have to worry about is just this guy over here, right? This is essentially a linear response matrix, right? This quantity is a key quantity, of course, in statistical physics that comes up again and again. This is called the susceptibility, or this is a susceptibility matrix, right? And we're going to call this matrix new. And so this entry is the new jkth entry of this matrix. And what this is essentially saying or asking is, if I make a small change to the carrying capacity of species K, how much does that affect the steady state abundance of species J? Right? That's what this susceptibility is saying. How susceptible is the system to making changes in some parameter? Okay, and do we know what this matrix is? We don't know, right? So seems like we've introduced a new unknown into the problem. And so that's something that we're going to have to compute. We're going to have to compute this entire matrix, but we'll see that it'll turn out that we'll be able to do it. Okay, so this, just to remind you, is an unknown currently. We don't know what these news are, but we'll find it later. So I've written it down in my roster of things to compute later. Okay, and this delta KK is what? Minus AI0 N0. Right, that's how much I change. Well, that's AK0 N0, right? That's the change in the carrying capacity of species K. This was for species I. Okay, all right. So we've computed something modulo some unknowns. How the abundances of all the species after the cavity perturbation change and relate to the abundances before the perturbation, right? What do we have left? We have step 4, which is now we have to ask, how do all of these changes to all the species abundances come back and affect the cavity species? And this is going to be the key part of this entire calculation. Okay, so now all I'm going to write down is again the steady state condition for a species we haven't written down before, which is N0 dot, right? So whenever this cavity species reaches, whenever the system reaches steady state, the cavity species also needs to have its dynamics such that N0 dot is 0. And so what that means is that this quantity is going to be 0. And here I'm not missing another term, right? This is just how every species J affects this cavity species 0, right? This, of course, I know how to write down because I know what my ensemble is. This was the key quantity I didn't know, right? So at some new steady state, there'll be a new set of abundances, but I just computed that here, right? So I basically substitute this in over here, and then we will be done. So I just, that equation is going to be important. I want to write it down separately. Where should I write it down? Actually, maybe let me write it down here, and then I'll write the full thing over separately. So what this is going to give me is it's going to give me K0 minus N0 minus sum of A0J, Nj without 0, plus sum of A0j, AK0, nu jk, and 0. This is a sum over jk. Okay, all I did was I substituted this nj over here. This I started calling nu jk, and I just substituted delta kk as minus ak0 and n0. So this minus became a plus. And that's what I ended up with. Everyone feeling okay about this equation? Okay. Okay, now all I'll do is I'll essentially do a little substitution, and then we'll discuss what it means. Really didn't want to have to erase this bit over here. Is it okay if I write down stuff over there? Okay, all this is going to let me do is going to let me write down n0 as the following thing. It's going to be the maximum between 0 and algebra that, again, you guys are better than me at. Okay, so I did two things over here, so let me clarify. One thing is this max that looks like a funny thing. That just comes from what we just discussed about these equations, right? So in these equations, to get this to be the LHS to be 0 or the RHS to be 0, you can either have N0 be 0, or you can have this quantity over here be 0, right? When N0 is 0, this quantity over here, my argument is, must be negative. Why is that? What if it were positive? That's what I'm assuming when I'm writing down this max, right? I'm kind of assuming that N0 finally, the solution to this, will either be 0 or it will be something else that I think of as a positive number, right? So the argument is that when this N0 is 0, this better be negative, and that comes from this uninvasibility that we were talking about yesterday, right? Which is when a species is dead, right? That's when N0 is 0. Should not be able to invade this system. We're looking for uninvadable fixed points. And if that's the case, then this whole thing over here that gives us the growth rate of the species should then be negative. Right? If it were positive, that means at very low abundance, the species will be able to invade. So the uninvasibility of these fixed points is what gives us the fact that this N0 in the end is either 0 because the species went extinct, or some other positive number. And if this second part is confusing you, well, you all know again how to solve linear equations. So if N0 is not 0, then this thing is 0. And then I just rearrange stuff over there. This is really the central equation that we'll work with over the next hour or two, which will stretch over to the next class. Okay? We have now an equation for the abundance of N0. And ideally, I would like to say it's only in terms of things that we know, but that's not currently the case, right? There are NJs without 0 hanging around. There are new JKs hanging around that we don't know. So we're not quite done yet, right? But this is this is a central equation that we will be looking at for the next hour and a half. So let's kind of get used to it. So before we sort of proceed, are there any questions about this equation itself? Okay, everyone's okay with the 4 steps that we've sort of done here? We won't get to the 5th step today. Okay, have I substituted anything about my ensemble so far? No, right? I haven't. There are no mu's here, no sigmas, no k's, no sigma k's. So let's do that now. That's just some, this is in some sense the general solution. that you will always get for this model, no matter what ensemble that you use. But now let's substitute our ensemble. Okay, so I'm going to substitute, so of course the K0 is going to be simple. That's just going to be some K plus sigma K delta K0. So I won't think about that for now. I really, when I substitute this ensemble, I'll have to substitute it in each of these sums, right? And it's going to get a little bit involved and hairy if I just keep hanging around this entire fraction. So I'm just going to do out the sums term by term. Okay, so let's kind of focus on things term by term. So let's just focus on this term first. Let's focus on the denominator first, because actually, I mean, we could have done it in any order. I'm just choosing to do it with the denominator first. This is JK, just to remind you, this is a double sum. I'm just writing down one sigma over here, right? So what's going to happen to this is A0J is a random variable. This AK0 is a random variable. New JK, well, I don't know what it is, right? But this is a sum over a product, which is itself some random variable, right? It's a sum of many, many random variables. And so in some sense, I mean, this sum will itself be a random variable. So we can ask for what its moments are. Okay, so let's just compute the moments of this random variable. We can compute the first moment of this random variable. And how would we do it? Maybe before I just compute the moment, let me just convince you that this is the case. So let's write it down explicitly. This A0J is going to be mu over S sigma A0J, where this is a little a. Second one is going to be mu over S times sigma AK0, little a. This is mu JK. If I do this out, and if I did it correctly, I'll find that something is mu square over S squared times sum of mu JK plus mu sigma over S sum over JK AK0 mu JK plus A0J mu JK. Do we agree? Did I write it down correctly? I think I messed something up. Oh, there's one more term. Sigma squared mu JK A0J AK0. Okay, I mean, this is all simple algebra. There are 4 terms over here. And now you can see that there are all sorts of S's, S squares, etc., hanging around. We're working in a large S limit, right? So we'll really only care about the leading order terms. We won't care about any sub-leading terms. And so let's sort of look at this part term by term. What do you think of this guy? Okay, what's the argument? This is 1 over S squared. So maybe we should drop it. Is someone concerned about this guy over here? How many terms is this summing over? Summing over S squared terms, right? So maybe in principle you would have to worry about it, right? It's S squared terms being added up. It'll turn out though, and I'll convince you tomorrow, that this term actually does drop out because this average itself is actually not something that contributes. What else? What about this guy over here? Well, I guess this is 1 over S, but I guess it again depends on what happens to this quantity, right? So again, we're going to have to worry about this quantity over here. I don't know if I'm going to have to be able to go through all of these arguments in time. So let's Let's see where we go. I'm going to erase out this bit over here. Okay, so let's just focus on worrying about this quantity first. This is nu jk a0j ak0 with a sigma squared sitting outside. And what is it really? It's really sigma squared times, I just write down nu1, 1. I just like to write down a few of these terms, right? This is a01, a10 plus nu1, 2, a01, a20 plus blah, 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 right? And if we want to compute now the moments of this guy, we'll really be computing the moments of every single one of these terms. Yeah? So if I compute the moment of this guy, I really am going over the sums over all of these things. Right? So just to kind of remind you and do a few more of these, I'll do all of those. I'll get nu11, a02, a20, nu21, a02, a10, and so on. What do you think will happen to terms of this kind? Well, if I just imagine that the news are not correlated with the little a's, then really I'm sort of left with this, right? And this we know from our ensemble, right? This kind of thing only had two contributions, either when ij is KL or when you have diagonally opposite things. This is neither, right? These all go to 0. These all go to 0. The only things that are left over are actually these diagonally opposite entries, right? This is a01, a10, a02, a20, and so on and so forth. And how many of these terms do we have? This in the end is sigma squared times some mean of nu ii, the mean of the diagonal entries of the susceptibility matrix, times whatever this quantity is, right? And what is this from our ensemble? Rho over S, right? And this is a sum over how many quantities? S, right? Not S squared, because all of the off-diagonal entries went away, right? So this is this times this times this times this, S times. So the S and the S cancel. And you're left with sigma squared rho and a quantity that's basically the mean of the diagonal entries of this matrix, right? So you can also think of this quantity as taking the trace of this susceptibility matrix and computing its average, right? That's a quantity we're going to call just nu. Okay, the nu ij was this whole matrix, but now what it turns out, the only thing that we really actually need to care about is the mean of the diagonal entries, right? This is the mean of the diagonal entries of the susceptibility matrix. Okay, so that's, and what I'll leave to you is to show that these terms will also be subleading in the largest limit. These are all subleading. you can essentially carry forth the same arguments that we use for all of these terms to sort of get that. Because now we know that this last term over here is an order 1 term, right? So anything that's sort of not order 1 is going to go away. And so you're going to find that these all will go away. And so now we know that basically this guy over here, we can replace with just a number sigma square rho nu. I haven't computed the second moment of this quantity. I'll again leave it to you as homework, or we can discuss today in the tutorial. How do you show that this quantity is actually self-averaging? Which is to say, in other words, that its fluctuations vanish in the largest limit. So there's really no other fluctuation term that I have to write down here. I just have this. I'm only now left with this thing over here, right? And this we can actually talk about in the next 1 minute. So here also I would have to substitute my ensemble for A0J. But just like we were talking about here, this is a random variable, this is a random variable, this product is some other random variable. And so sum of many random variables is what we have over on the top over here, right? Do we know something about the sum of many random variables? Right, so the central limit theorem might apply. And why do you say might? What are the conditions in which it applies? Yes, so you have to somehow convince yourself that each of these entries is independent, identically distributed. They come from the same distribution and they're independent of each other. The identically distributed, I guess, is not too hard to see, but the independence, we can just argue now, right? So this A0J is what? This is how species J affects species 0, right? This is how every species affects the cavity species. What is Nj without 0? That's the abundance of the jth species in the absence of the cavity species, right? So this thing over here, does it care about the cavity species? No. This thing over here is actually only well defined once you have the cavity species. So how could these know anything about each other, right? So these are two uncorrelated random variables. So of course their product would be uncorrelated as well. And so you have a sum of many independent random variables which you expect under the central limit theorem to be Gaussian, right? This is a Gaussian random variable. And what we are left to compute is what are its mean and variance, right? So we'll do that in the next class. But before we end, my last question to you is this question of universality that we were talking about at the beginning of this class, right? In the end, we got this guy to be a Gaussian random variable. Did that depend on whether A0J was picked to be Gaussian or something else? No, right? It could have been a uniform distribution. The only thing it couldn't have been was a distribution with ill-defined first and second moment, right? That's the other condition you need for the central limit theorem to apply, right? So in some sense, actually, here we really haven't used the Gaussianity of the A0Js much at all. Actually, you can also convince yourself that this thing over here does also not invoke the Gaussianity of the A's. So actually, nowhere here have we invoked the fact that A's are Gaussian. They're just something that we use for ourselves to kind of get a sense of what we build. But this result over here, the fact that this is Gaussian and this thing is the way it is independent of the exact distribution of the Aij's. And so in some sense, this result over here and whatever distribution that we'll get out of it will also be a universal distribution under the assumptions of the statistics of the ensemble that we have. Okay? This relies on the fact that this perturbation is small, which will be satisfied for a large system. Yeah. So for large systems, this works. Right? For small systems, of course, like if you try to use this for the two species calculation that we were doing yesterday, you will fail. Because any one species that you add to a system of any one other species is not going to be a small perturbation. The nature of which distribution? The N0 distribution? Yes, again, the nature of the ensemble will come in through the moments that you have, right? So that's the only thing that matters. I'm saying the form of the distribution doesn't matter. Okay, so tomorrow what we'll do is that we'll pick up here, which is that we'll pick up at this solution. We'll just finish off computing the moments of this Gaussian random variable. You can also do this. Just substitute in what you know for A0J. You'll introduce new unknowns, right? Those will be unknowns for what the mean and the variance of this N distribution is, which you don't know. That's going to add some other unknowns to this, but in the end, we're all going to be able to compute that. So tomorrow what we'll do is actually start off here, finish off computing all these quantities that we wanted to compute, and then plot the phase diagram for this model. Okay? All right, I'll see you guys at the tutorial later today and then in class tomorrow.